Unit 7 for geometry is going to be all about algebraic expressions. Section 1 has to do with exponents. So first we're going to go over some rules of exponents. Now first off we have the product of powers rules. So what this says is if we have some number a, that's our base number in both cases. In each case it's to a different power, so a to the b and a to the c. And if we multiply those powers, so a to the b times a to the c, the answer is just going to be a to the power of b plus c. So anytime that they have the same base and they're being multiplied, you can just add these powers. So as an example, we can take 3 to the 4th power times 3 to the 5th power. That's going to be 3 to the 4 plus 5, so it's going to be 3 to the 9. And another way to kind of show that, 3 to the 4th means 3 times 3 times 3 times 3 times 3 to the 5th is 3 times 3 times 3 times 3 times 3. So really we have 9 of these 3's being multiplied together. So 3 to the 9th power. Now again, this only works if the base is the same. So this 3 on bottom has to be the same. And if this is multiplying. If it is subtracting, adding, those don't really do anything. You have to find each piece individually and then subtract them or add them. If it is dividing, it's something else. There is a different rule for that. In fact, that'll be this rule, the quotient of powers rule. A to the power of b divided by a to the power of c equals a to the power of b minus c. So when we were multiplying these, you add the powers. When we are dividing these, you subtract the powers. So to see an example, 3 to the 6th over 3 to the 4th equals 3 to the 6 minus 4, so it's 3 squared, which we could also just call 9, right, equals 9 in the end. And again, a way to see that, 3 to the 6 is 3 times 3 times 3 times 3 times 3 times 3, so there's 6 of them. 3 to the 4th is 3 times 3 times 3 times 3, so there's 4 of them. Anytime that we're just multiplying on top and dividing by something being multiplied on bottom, we can divide things out or cancel them out. So 3 cancels with 3, 3 cancels with 3, 3 and 3, 3 and 3. So what's left over? There's like a 1 left over times 1 down here. 3 times 3 over 1, which is the same as 3 squared over 1, or just 3 squared. Or again, like we said, that would just be this 9. So that was the quotient of powers rule. We also have the power of a power rule. And that says that if we take some base a to the power of b, then in parentheses we take all of that to the power of c, that would be the same as a to the power of b times c. So 3 squared to the 3rd power would just be the same as 3 to the power of 2 times 3, which is 3 to the 6th power. And again, we can see that because, I'm going to use purple here, this piece right here, 3 squared, means 3 times 3. Happens once, twice, 3 times. Why does it happen 3 times? Because it's to the 3rd power. 3 squared, so 3 times 3. Do that 3 times, so 3 times 3, 3 times 3, 3 times 3. Multiply them all together. We'll notice there are 6 of them, 3 to the 6th power. That's power of a power rule. Power of a product rule. So a times b, in parentheses, to the c power. Well, we can apply that power of c to each of these pieces individually. Again, as long as this is just multiplying between them. If it is add or subtract, we cannot use this power. It only works when this is a multiply. But it would become a to the c power times b to the c power. So for an example, 2 times 3 to the 2nd power, that means 2 to the 2nd power times 3 to the 2nd power. 2 to the 2nd power is 4, 3 to the 2nd power is 9, 4 times 9 is just 36. Now to double check and make sure this works, oops, actually I want to leave that one away. 2 times 3 is just 6, and 6 to the 2nd power, or 6 squared, is 36. So that double checks pretty easily. Let's look at another example, though. Instead of 2 times 3, so we have two numbers being multiplied, let's do 2 times x. So it's a number and a variable. If it's 2x and all of that is being squared, again, we would apply that squared to each of these pieces. 2 squared times x squared. 2 squared is 4. X squared is just x squared. So we call it 4x squared. So again, that's power of a product rule. Power of a quotient rule means that we have a quotient inside here, so a divided by b, or a over b, and this whole thing is in parentheses to the power of c. Now, kind of like our power of a product rule, that c gets applied to each piece individually. So to the whole numerator and to the whole denominator. So a to the c over b to the c. So let's see an example of that. 5/3, 5 over 3, squared. So that whole thing to the second power means 5 to the second power over 3 to the second power. So again, we're just squaring each piece, 25 over 9. The 0 power rule. This one actually has two parts. Anything to the 0th power equals 1. So any number you can think of, a to the 0th power just equals 1. Another part of the 0 power rule means 0 to any power just equals 0. Because again, that's just saying 0 times 0 times 0 times 0 times 0 as many times as you want, so it's just going to be 0. So some examples. Instead of a, if I replace it with 4, 4 to the 0th power, it's just 1. 0 to the 7th power means 0 times 0 times 0 times 0 times 0, 7 of them. That's still just 0. So if it's to the 0th power, it's 1. If it's 0 to some power, it's 0. Now the question might come up, what about if it's 0 to the 0th power? Would it be 1 or would it be 0? And the answer is, that answer does not exist. It's kind of like dividing by 0. If you were to take some number and try to divide it by 0, you'd get an error on your calculator screen because it's indeterminate. You can't do 0 divided by 0, or you can't do anything divided by 0. You also can't do 0 to the 0th power. That answer will not exist. Let's look at the negative power rule. So any number to a negative power, so like a to the negative b, means you just do 1 over that amount. In a sense, this basically just means if it was in the numerator, put it in the denominator and make it a positive power. If it was in the denominator, move it to the numerator. So negatives on bottom go up, negatives on bottom go down. So let's see what this looks like. If we have 3 to the negative 2 power, that's the same as 1 over 3 squared. So we just call it 1 over 9. And again, what I mean by flipping that is, think of this as 3 to the negative 2 over 1. The negative 2 means we're flipping these around. So we'd have 1 on top over 3 to the second power. It's not that this 1 moved up here. It's that this 3 to the negative 2 became 3 squared to the positive 2 on bottom. And when you do that, it leaves 1 times this amount. Oops, I'm going to do a... So this 1 stays up here. 1 times 3 squared is just 3 squared, so this one went away. But in the end, negatives basically just make it a fraction, or flip it from numerator to denominator. We're going to do a quick review on radicals. So that's like square roots and cube roots, etc. When you have something written like this, it might be kind of hard to see there, so I'm going to write it over here. Cubic root of 4 squared. This 3 on the outside is what's called the index. So that means it's a cubic root. So it's saying what times itself 3 times gets us to that answer. This kind of squiggly box thing is called the radical sign or radical symbol. In this case, we'd call the 2 a power or an exponent. It's 4 to the power of 2. The 4 itself is called a base because it's 4 to the power of. The whole thing underneath the radical sign, so this whole thing, 4 squared, is what's called the radicand. Okay, so those are just some pieces of terminology that we might go over, we might use when talking about radicals. So just a quick review. We're going to need that for the fraction power rule, which is if we have a number like a to the power of a fractional exponent, so a to the power of b over c. This number c becomes that index on the outside. So it's this number out here. This number b becomes the power of a. So it's a to the b power under the square root that has the, or maybe not a square root, but under the radical symbol that has c as an index. Or, another way to look at this, a to the b over c, you can do the index c of the square root, or cube root, or whatever root it is of a, to the power of b, but that power being on the outside. Technically, these mean the same exact thing. These will come out to the same answer every single time. So you can take that root of a and then put it to that power, or you can go a to that power and then take that root of it. So I'm going to show you an example of what I mean here. 8 to the 2/3 power means that I can do 8 squared and then find the cubic root of it. Well, 8 squared is 64, and the cubic root of 64 means what times itself equals 64? Well, that'd be 4. 4 times 4 times 4 is 64. So that was one way to look at it. The other way to look at it is 8 to the 2/3 power means take the cubic root of 8 from this 3, and whatever answer we get there, we're going to square it. Well, the cubic root of 8 is 2, because 2 times 2 times 2 equals 8. And then when we square that, 2 squared is 4. Either way, notice that we come out to the same answer of 4. 8 to the 2/3 power is 4. Let's go over some more examples here. Our first example, in parentheses, a, or 3 times a to the negative 2nd power, all of that times 5 times a to the 4th power. Simplifying this out, because there are no exponents on the outside of these parentheses, we just multiply each piece together. So we look at our coefficients, 3 and 5. Right here, those are just the numbers. And then we look at our variables, a to the negative 2 and a to the 4. So 3 times 5 times a to the negative 2 times a to the 4th. Well, 3 times 5 is 15. And when we do a to the negative 2 times a to the 4th, that is a product of powers, so we add them. Negative 2 plus positive 4 is positive 2. So 15a squared. In our next example, we've got 5x squared in parentheses to the power of negative 2. That means we have to do this negative 2 power to each piece. And again, this is going to go to each base. 5 is a base, x is a base. Now 5 has kind of a hidden power of 1 right now. It's 5 to the 1st power. So we have to do 5 to the power of 1 times negative 2. X had a power of 2 already, so it's x to the power of 2 times negative 2. Because this negative 2 on the outside means multiply by each of those powers that are already there. So 5 to the 1 times negative 2 is going to be 5 to the negative 2. X to the power of 2 times negative 2 is going to be x to the negative 4. Well, 5 to the negative 2 is going to change things up. That's going to mean move it down because it is negative and keep it as 5 squared. X to the negative 4, same thing, because it's negative, means move down. So we go into the denominator. So there's nothing left in the numerator, so it's just 1. 1 over 5 squared times x to the 4th. Simplifying that one last time, that's 1 over 5 squared is 25, and x to the 4th is x to the 4th, so 1 over 25x to the 4th. Our next example is 5 times y to the negative 3. Well, 5 is just kind of all on its own. It's 5 times some amount here. Since it's y to the negative 3, remember that negative means we have to move it down. So it's 5 times 1 over y to the 3rd power. Now if it helps you to think about this, call this 5 over 1. Remember, any whole number, you can just call that amount over 1. In fact, you could even do that with any variable. If we had, let's say, x squared You could call that x squared over 1 if you wanted. Get rid of that. So if we have 5 over 1 times 1 over y cubed, multiplying fractions just goes right across, so 5 times 1 is 5. 1 times y to the third is y to the third. So our final answer is 5 over y to the third power. We always want our end answers to have positive exponents in the end. So even if that puts them underneath like this, we just want those exponents to be positive. In our next example, we have 27f to the 5, g to the negative 4, all of that to the 0 power. Now, we could do 0 times this, 0 times this, and 0 with this one. Remember, this is 27 to the first power, so it's 27 to the 1 times 0. 5 to the 5 times 0. G to the power of negative 4 times 0. Each one of those pieces then would become 27 to the 0, f to the 0, g to the 0. In the end, each of those would just be 1. So it would be 1 times 1 times 1. So our answer would just become 1. Now, kind of a trick for that is whatever answer this whole thing becomes in the parentheses, that whole number is being to the power of 0. And we know that anything to the power of 0 is just simply 1. So anytime that you have a big thing in parentheses, all these numbers to the power of 0, you know right away that that piece is just 1. All right, looking at our next example, we have 3 times z to the negative 4, all of that to the power of 2, and we have that multiplied by negative 5z cubed. Simplifying that out, we take the 2 and we have to apply it to each of these bases. So 3 to the power of 2 and z to the power of negative 8. I did negative 8 because it's negative 4 times positive 2. And remember, when it's power to a power, we multiply. If it was power times another power, that's when we add. So we multiplied this time, 3 to the 1. 1 times 2 is 2. Z to the negative 4. Negative 4 times 2 is negative 8. Now we can simplify it and just put everything multiplied together. So 3 squared from right here times negative 5 from right here times z to the negative 8 from right here times z to the 3 from right here. Now simplifying some of these, 3 squared is just 9. And we see that these will have the same base, negative 8 and z in one case to the negative 8 and z in one case to the positive 3. So we change this to 9 times negative 5 times z to the negative 5. Because it was power times another power, we do negative 8 plus 3. We add them up, and that's how we get to negative 5. From there, we have 9 times negative 5 is negative 45 times 1 over z to the 5th. Because this was a negative power, it's 1 over that amount. So our final answer is negative 45 over z to the 5th. Again, if it helps, do this. Negative 45 over 1. So that when you multiply, you just go right across. Our next example, 3y squared over y to the negative 4. All of that is being cubed, or to the power of 3. So when this is cubed, and it's a quotient, that means we're cubing each piece. So the numerator and the denominator. This 3 is getting applied on top and on bottom. So it'll look something like this. Once we have it there, we can simplify each piece. This 3 needs to go to each base, so here and here. So it becomes 3 to the power of 3 and y to the power of 6, because 2 times 3 is 6. This 3 needs to get applied just to the one base here, so it becomes y to the negative 12 on bottom. So here's our numerator, here's our denominator. Simplifying that out, 3 cubed is 27, 3 times 3 times 3 is 27. Y to the 6 over y to the negative 12. Remember our quotient rule, if these are the same base, one on top and one on bottom, you take the top, subtract whatever's on bottom. So 6 minus negative 12, which in the end will become 18. So we have 27y to the 18th power. And we have another example. 3a squared b to the negative 3, all of that squared, or to the second power, and all of that divided by, or over, 9a to the negative 2, b to the 3, c to the 4. So simplifying one piece at a time, this 2 needs to get applied to each of those base. So 3 to the 2, a to the 4, b to the negative 6. So we did 2 times each of these powers. Remember, this was kind of a hidden 3 to the power of 1. From there, we can start simplifying by moving things. A is on top and a is on bottom. So we would do 4 minus negative 2. Same thing, we have b as a negative 6 and b as a 3, so we do b to the negative 6 minus 3. And this 3 squared, we just say is 9. So when we actually go through that subtraction, 4 minus negative 2 becomes 6. Negative 6 minus 3 becomes negative 9. Also, because all of these are just being multiplied, we can cross out 9 and 9. We won't need those anymore. Because this b is a negative 9, it needs to move down. So we can say in the end that it's a to the 6 over b to the positive 9, c to the positive 4th. And this would be our most simplified answer. When we are working with radicals, we need to factor or break down the radicals so that they can cancel with the index. And we'll leave anything that's left over underneath that radical sign. So by that I mean, in this case, if we have the square root of x squared, remember that means there's a radical of 2. So we want to break this up into powers of 2, and it already is 1, x squared. So we can just cancel out index with that power. We would know that the only thing left over is x. So our answer is x. Now in this one we have the cubic root of 16x to the 4th. Now 16x to the 4th, 16 is the same as 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is, 16. X to the 4th is just x times x times x times x. Now that we have these broken up, we can group them into groups of 3. So these 3 2's become 2 to the 3rd power. These 3 x's becomes x to the 3rd power. And we still have a 2 and an x left over. So 2 to the 3rd times another 2, x to the 3rd times another x, and we have that index here of 3. Well, now everywhere that we have a power of 3 cancels out and those come outside. So we'd have 2 and x on the outside of our radical. So 2x times the cubic root of, and then just whatever's left over. 2 times x, or 2x. So this would be how to simplify our radicals. So if we have a radical like this, cubic root of 27x to the 6th, all of that squared. Well, we're going to worry about squaring things at the very end. So I'm going to put those in kind of a red parentheses with the squared on the outside. And we're going to break down underneath the radical sign, so that radicand, like we did before. 27 is 3 times 3 times 3. X to the 6 is x times x times x times x times x times x. Group those into 3's. 3 times 3 times 3. So 3 to the 3rd power. X times x times x. So x to the 3rd power. And another x times x times x. So another x to the 3rd power. So each of these pieces is to the 3rd power, so we can cancel out everything. That index with that, with that, with that. And it's like they're all coming outside of the radical. So it's 3 times x times x. All of that is being squared. Well, 3 times x is just 3 times x squared. And all of that is being squared. So we apply it to each piece. 2 times, or power of 2 with this 3. Power of 2 with this 2. 2 times 2 is 4. So 3 squared times x to the 4th becomes 9x to the 4th. I'm going to go over 2 more examples that will help make some of the homework problems go a little easier. This one I'm going to show you 2 ways to do it. If we have 4 and then in parentheses to the power of 2, all of that in parentheses to the power of 3 We can do that two ways. We can say 4 squared is 16, and 16 cubed then, to that power of 3, is 4096. That is one way to do it. Or, to make it easier, you can do 2 times 3 right away, because it's power to a power, and say that it's 4 to the 6th power. 4 to the 6th power is still 4096. So either way will get you there. In this one, we have 16 to a negative fraction, 16 to the power of negative 1/2. So we went over fractional powers a little bit and how they look with radicals, but we're going to see what it looks like especially with a negative fraction. Because it's negative, that means we switch it so it moves down. So I guess what we could say if we wanted to at first is that it's 1 over 16 to the 1/2 power. We could do that first if we wanted to. Once it's 1 over 16 to the 1/2 power, we do 1 over because it was negative, so that took care of the negative part. Now 16 to the 1/2 power, this, remember, is the power of our base 16, so 16 to the 1. This is the index of the radical, so 2. The 2 square root, or 2 radical sign, just means the square root, so we really don't need the 2 there, so it just means square root of. 16 to the power of 1 is still just 16, so we don't really need that there. So really what we're looking for is 1 over the square root of 16. We know the square root of 16 is 4. So this is just 1 over 4, or 1/4. And that'll conclude our first video.